Hey, Dr. Clark coming at you with a differential equations video. In this one, we're looking at section 3.3, modeling with systems of differential equations. So what's all about these systems? Let's take a look. So there's lots of situations where you might have a system of differential equations. For example, during the COVID-19, that was modeled using what they call an SIR model, susceptible, infected, and recovered. And you sort of have these three buckets. And that was, somewhat useful for modeling, but obviously it's a little bit coarse, but it turns out it does actually work somewhat well. In cancer research, you got your cancerous B cells and you got your T cells that are killing the cancer, and sort of one's trying to grow and the other's trying to kill it. You got a system. You got two different cells that are interactive. We're going to look at multiple radioactive elements in a decay chain, foxes and rabbits. I think we talked about this loosely another time. Position and velocity. This is a huge one. We're going to spend a lot of time this year on position and velocity. And then, humans and zombies. You got your humans, you got your zombies. It's kind of like an SIR model, although the R in this case is not a great situation often. But you can model humans and zombies using differential equations. It's been done. And people have written papers about this. All right, so we're going to start with something a little more standard, though. We're going to look at coupled mixtures. So in this problem, we've got a coupled tank setup. Now, you got tank 1, you got tank 2. What's interesting is tank 2 pumps into tank 1 pumps into tank 2. So you got mixing happening here, and then you got a drain on tank 2 and a water coming into tank 1. Can we cook up a model for this? So the question is, we're going to let A of T equal the salt in tank 1, or tank A, I should say, and we'll let B of T equal the salt in tank B. And then what we need is a differential equation, dA dt equals, and dB dt equals. And both of these are going to be in minus out, in minus out. What's interesting about the coupled setup is that you end up with, if it goes out of A, it went into B. And so you have a minus term becomes a plus term, okay? But everything else is essentially the same as what we've done before when we've sort of solved these problems on, in the past where we just had single tanks. So let me just move this down here. The in minus out will kind of hop up and down and see if we can't write down the model. So it looks like we've got, first let's look at the flows. 3 in and 1 in, so that's 4 in, 4 out. So the volume on tank A is going to be basically held constant. So I'm just going to say VA equals volume of tank A. And then let's look at tank B here. 3 out, 1 out, so that's 4 out. And then you got 4 in, 4 out, 4 in. So the volume on tank B is also constant. So they didn't tell us what it is, but that doesn't matter. We can just define it to be VB and VA, the volumes of the specific tanks. Okay, so A, let's do the in. I've got 0 coming in here. This is pure water coming in. I've got a mixture coming in at 1 gallon. So the flow rate is 1 gallon per minute. That's the flow. Times B grams of salt divided by the volume of tank B. That would be in grams per gallon. And then, of course, you get basically grams per minute, which is what you need for the units. So it's basically just, maybe I'll just slide this down and we can have a clean version and a dirty version. So this is just B over VB in this case. And then we've got 4 coming out. So we're going to lose 4 gallons per minute, and it's going to be A over VA grams per gallon. So we're basically just going to subtract 4A over whatever VA is. And that is the differential equation for dA dt. Okay? B over VB minus 4A over VA. Now, it's a system, right? It's a system because it has the A equation has A's and B's in it, right? A and B are functions up here, remember? And we've got two of them, and so they both show up. Everything that went out of A went into B. So we're going to have a plus 4A over V sub A coming into B, right? Look right here. Everything that went out of A went into B. So that term is repeated as an out and then an in. And we lose out of B, well, we lose 1 gallon there and 3 gallons there, so we're losing 4 gallons. 4 times B over VB. 4 gallons out per minute, B over VB gallons or grams per gallon. And that there is a what you'd call a, well, that's our model. Okay? So that is the model. It is a system of two differential equations. To kidney dialysis, what happens is you have somebody whose kidneys aren't working as well as they should. They hook them up to a dialysis machine. It pumps their blood out of their body. It goes through a machine that cleans it and pumps it back in. And they essentially what they do is there is a semi-permeable membrane right here. And the things in the blood, I think it's the urea mostly, passes through that semi-permeable membrane, and then, the urea scrubber, and then it comes out and it gets removed and thrown away as waste. And so as the blood goes through, the urea comes out, and then it comes away, and then you got clean blood. And you could theoretically run these suckers both in the same direction, or you could do it counter currently, one way and one the other way. And if you run the math on this, they did it. It turns out that you get better effects from running it in counter current. And the reason for that is right here. This is the dirtiest blood here. Here's dirty. And this would be the cleanest blood. And here would be the dirtiest urea scrubber. And here is the clean. And so what you get is no matter how dirty the blood is on the front end and no matter how dirty the urea scrubber is, it's dirty with dirty, so you still can pass through, and clean with clean, of course, you can still pass through. So if you run it the other way, you have the clean blood with the dirty scrubber, and then you won't have that gradient, and so it won't pass through. And so basically, it's the same kind of a tank. You've got N tanks and M tanks, and you could basically run it, and they ran it and checked the math, and it turns out this is more effective. And so that's how they do it. So these, salt mixture problems look made up, but it turns out they're kind of real. Okay. Now this is a check your understanding problem. I think I pulled this off an old exam. So you can try this one. And what I would recommend is pause the video, try the problem, and then come back and see if you got it right. I'll walk through the solution in a minute here. Pause the video, see if you can do it, and then we'll do it together. All right, so if you tried it, then hopefully you've got an answer, and you can check your work with mine. If you want to fast forward to the end and see if you got the right answer, and then back the truck up to see if you got something wrong in the explanation, or just kind of watch through. Either way. Tank A and Tank B are set up with the following conditions. Create an initial value problem to model the amount of salt A and B in grams in each tank. Both tanks are well mixed. A is filled with 200 liters of salt brine concentrated at 2 grams per liter. That feels like an initial condition to me. 200 liters, 2 grams per liter, that's 400 grams of salt in tank A. So I'm going to just start putting some stuff down. A of T equals grams of salt in tank A, and B of T equals grams of salt in tank B, and there's going to be an A of 0 equals 400 grams, and there should be a B of 0, and let's see, it's pure water in tank B, so that's 0. So those are my initial conditions. That's part of the model. The initial conditions are part of the model. We're going to need dA by dt, and we're going to need dB dt equals. That's the answer we're looking for. It didn't ask us for a solution. It asks us for a model, and a model in this case is a system of differential equations. We got the initial conditions already done. All right. Brine containing 7 grams per liter is pumped into tank A at a rate of 9 liters per minute. 7 grams per liter, 9 liters per minute. That's brine water coming in. 9 times 7 is 63. So every day we're getting 63 grams in to tank A. The mixture from tank A is pumped out into tank B at a rate of 5 liters per minute. So tank A is losing 5 liters per minute of water from A to B. So we're going to lose 5 liters per minute, A over volume of A. And that's going to go into tank B, so that's 5A over VA, right? Every salt that left A went into B, right? A into B. So this is a -5, that's a +5. It's the same thing, right? This is salt. It left. Where did it go? Into B. So those things are the same. So I think I checked this. The mixture from tank A is pumped into tank B. Check. The mixture from tank B is drained out at a rate of 5 liters per minute. Check. So we're losing 5 liters out of B, minus 5B over VB. Okay, now that's all fine and dandy if all we had to do was leave the volumes as is. We basically have, I think, A, we have B, we've got water coming in there, we've got water coming in there, and then we've got water coming out there. So basically we have 3 different things, and here's the water coming into A, there's that, here's the water coming from A to B, there's that, and here's the water coming out of B, there's that, right? So there's basically 3 little motions. But we should figure out the volume. So let's look at the volume of tank A. It's going to start at 200. We're going to gain 9 liters per minute, and we're going to lose 5 liters per minute. So that's going to be, we're gaining 4 liters per minute. So 200 plus 4t. 200 liters at the beginning, and every minute you gain 4 liters. So 200 plus 4t is VA. So I'm going to erase VA and write 200 plus 4t. We've done problems like this before, so hopefully that's somewhat familiar to you. Tank B, I think, is 5 in, 5 out, so that's holding constant, and it started at 500, so I'm just going to write 500 where VB was and call that good. And that there is a model. Got the initial conditions, got the differential equation. All right? And that's a mixing problem. So hopefully you got that one right. And if you did, you should feel good. So I'm going to pause it here for this video. And in the next video, we'll do a couple new problems. So we'll see you in the next video.